Not long ago, the sky above Earth began to glow in a way that most people had never seen in their lifetime. Not just near the poles, not just in the coldest regions, but in places like Florida, in Mexico, even in locations where that kind of light was never expected to appear. In 2024, one of the strongest geomagnetic storms in over 2 decades reached this planet. A storm powerful enough to force nearly half of the satellites in low Earth orbit to adjust their positions just to remain stable. And some were unable to recover. But what matters is that wasn't the most concerning part. Because if you take a closer look at what happened and at what has happened before, you begin to notice something different. The sun doesn't need to do anything new to fundamentally affect the world we live in. It only needs to repeat itself. In this video, we're going to take a closer look at what is actually happening with the sun, why even our best models can sometimes fall short, and the part that is rarely discussed is not a 12,000-year cycle, but something far more practical and possibly much closer than we think. If topics like this make you think more deeply, you can support Space Lull with a like and a subscription. Tonight, we're not just going to talk about the sun, but about the real limits of what we are able to understand. On certain nights in 2024, the sky over places like Florida, Texas, and even northern Mexico began to glow. Not city lights, not lightning, but slow-moving bands of red and green light, resembling auroras, a phenomenon typically seen only near Earth's polar regions. For many people, it was the first time in their lives seeing a sky like that. Photos were taken, shared online, and quickly spread. But beyond the initial curiosity, what was actually happening was far more complex. At the same time, space monitoring systems recorded a powerful geomagnetic storm, reaching G5, the highest level on the current scale. Some satellites in low Earth orbit began struggling to maintain stable altitude. Atmospheric drag increased as the upper atmosphere expanded due to energy from the sun. Some satellites were forced to activate their propulsion systems to adjust their orbits, and some lost the ability to maintain position. These are not theoretical scenarios. They were observed, measured, and reported. At a basic level, these phenomena can be explained relatively clearly. The sun continuously emits streams of charged particles. When these particles interact with Earth's magnetic field, they can trigger geomagnetic storms. Under sufficiently strong conditions, high-energy particles penetrate deeper into the atmosphere, creating auroras at lower latitudes than usual. That is why people in Florida were able to see lights that were once only visible in places like Alaska or Norway. From a physical standpoint, there is nothing unusual about what happened. Instruments recorded increased solar activity during this period. The number of major solar flares also rose significantly. Before the current solar cycle began, most predictive models had reached a fairly consistent conclusion. This cycle would be weak. Predictions suggested that the number of sunspots would remain below average, similar to the previous cycle, which was considered one of the weakest in decades. In other words, the general expectation was a relatively quiet phase. Fewer extreme events, fewer unusual fluctuations. And within that context, what happened in 2024 did not fully align. The issue is not that the models were completely wrong, but rather how we interpret their reliability. By 2023, real-world observations began to show a different trend. Sunspot numbers were higher than expected. Energy release events occurred more frequently. By 2024, activity levels had exceeded several predicted thresholds. This does not mean that science has failed, but it does suggest that current models do not yet capture the full system. There are aspects of solar activity that are still not fully understood, and more importantly, they may change faster than we expect. Even with the most advanced instruments, we are still observing the sun from a significant distance. We measure magnetic fields, we track sunspots, we record flares. But predicting exactly when a major event will occur remains an unsolved problem. There is no perfect early warning system. No model can predict every detail with certainty. And that leads to a simple reality. We understand quite a lot about how the sun works, but we do not fully control how it will behave next. If the current level of activity continues, phenomena like low-latitude auroras may occur more frequently. Stronger geomagnetic storms may happen. In most cases, these events cause only minor changes. But under certain conditions, they can lead to broader impacts, especially for systems that depend on satellite signals and large-scale power grids. For most people, these changes are not immediately noticeable. Daily life continues as usual. But something gradually becomes clearer. The modern world, with all its convenience and connectivity, depends heavily on systems operating above us. Systems that, in many cases, were not designed to handle rare but high-intensity events. This does not mean that a major disruption is certain to occur, but it does suggest that the stability we are familiar with is not always the default state of the system. And perhaps what matters most is not what happened in 2024, but how we interpret it. A rare event, observed, explained, and then quickly normalized, as if nothing had changed. But at some level, that may not be entirely true. Because sometimes the most important changes are not in what we see in the sky, but in the moment we begin to realize that it is no longer as normal as it once seemed. During the same period in 2024, beyond the visible phenomena like auroras, a series of other changes were also taking place, but received far less attention. Some commercial flights were forced to adjust their routes to avoid regions of higher than normal radiation along polar paths. GPS systems recorded minor signal deviations, particularly during the peak of the geomagnetic storm. A few regional power grids detected unusual induced currents, though not enough to cause major failures. There were no widespread blackouts. No system collapsed entirely, just small deviations, appearing briefly and then disappearing. These phenomena can be explained through relatively well-understood mechanisms. When a geomagnetic storm occurs, Earth's magnetic field becomes compressed and begins to fluctuate. These fluctuations generate induced currents in long conductive structures on the surface, such as power lines, pipelines, and communication cables. In most cases, these currents remain at low levels. They do not cause immediate damage, but they can alter voltage within systems, interfere with signals, or trigger protective mechanisms. For satellites, the issue comes from two main factors: radiation, which can affect sensitive electronic components, and the expansion of the upper atmosphere, which increases drag and gradually lowers orbital altitude. All of these effects have been studied and documented for decades. For most of that time, modern systems have been designed under the assumption that such events would rarely occur at extreme levels. Engineering standards are typically based on events recorded in the recent past. Risk scenarios are built around what is considered likely. In other words, systems are not designed for every possible situation, but for those deemed most probable. And for many years, this approach worked relatively well. No major failures, no prolonged disruptions. Over time, this created a sense of stability, that the system could regulate itself. The issue does not lie in individual components, but in the degree of interdependence between them. Power grids, satellites, the internet, and global positioning systems do not operate independently. They are connected in ways where a small change in one area can spread to others. A minor deviation in GPS signals can affect timing systems in financial networks. A satellite failure can reduce the accuracy of multiple dependent services. A small voltage fluctuation occurring at the wrong moment can trigger a chain reaction in protective systems. These events rarely happen at the same time, but when they do, the system no longer behaves in a linear way. And that is where simple models are no longer sufficient. We can simulate individual parts of the system. We can test components in isolation. But predicting exactly how the entire system will respond during a large-scale event remains an open problem. Not because of a lack of data, but because of complexity. A strong geomagnetic storm does not affect just one region. It can influence the entire planet at the same time. Systems across different countries, built to different standards, respond in different ways. And in some cases, those differences themselves become the hardest factor to predict. If an event strong enough were to occur, the impact would not necessarily come from a single cause. It could begin with a small shift in the magnetic field, spread into the power grid, affect satellites, and then return to the ground as a loss of connectivity. Not an immediate collapse, but a sequence of disruptions occurring close together in time and difficult to control once they begin. In an interconnected system, the weakness does not lie in any single part, but in the way those parts are connected. At an individual level, most of these changes are not directly noticeable. There are no clear warning signals, no obvious signs. But there is a simple reality. Most of what we rely on every day, from electricity to signals to data, depends on systems operating beyond our direct awareness. And those systems do not always operate under ideal conditions. This does not mean there is a reason for immediate concern, but it does suggest that the stability we experience is the result of multiple conditions being maintained at the same time. And when one of those conditions shifts, the system as a whole can respond. For most of the time, these systems operate almost invisibly. They do not draw attention. They do not create a sense of instability. And because of that, they are often taken for granted. But when small deviations begin to appear, even briefly, they may point to something much simpler, that the stability we experience is not the default state, but a state that must be continuously maintained. After unusual auroras and minor system disruptions were recorded, most of the attention quickly returned to normal. News coverage faded, the graphs declined, and what remained was mostly data. In 2024, the number of X-class solar flares, the highest category on the scale, increased significantly compared to the previous period. Some reached intensity levels not commonly seen in many years. At the same time, the number of sunspots, a direct indicator of solar activity, exceeded the initial predictions for the cycle. These were not changes large enough to cause immediate disruption, but they were enough to raise a question. What we are observing, is it really within expected limits? Solar activity is continuously monitored through multiple indicators: sunspot counts, radiation intensity, flare frequency, the speed and mass of coronal ejections. These are not assumptions. They are measured by dedicated satellites and observation stations around the world. And when compared with earlier predictive models, one point begins to stand out. Actual activity levels are higher than expected. Not at every moment, not in a clearly defined pattern, but enough to create a noticeable deviation when viewed over a longer period of time. In most cases, deviations like these are considered normal. The sun is not a linear system. Its cycles fluctuate naturally. So a cycle turning out stronger or weaker than predicted is not unprecedented. Within that framework, the common explanation is straightforward. This is a temporary variation within an acceptable range, a minor adjustment within a larger system. The issue does not lie in any single data point. It lies in how those data points are combined. When each data set is viewed independently, sunspot counts, flare activity, geomagnetic events, each can be explained on its own. But when they are placed side by side within the same time frame, a different pattern begins to emerge. Not one large deviation, but multiple small deviations moving in the same direction. And when multiple variables shift together, the likelihood of coincidence becomes smaller. This is not a conclusion, but it is a signal. A signal that the system may be operating in a way that does not fully align with the models we have built. We can measure what is happening on the surface of the sun with high precision, but understanding the full internal process remains limited. Convective flows, deep magnetic fields, and the interactions between different layers of the sun are not directly observable. Most current models rely on interpreting surface data. That approach is not incorrect, but it does mean there are still unseen components, and in complex systems, those unseen components are often the most important. If these deviations continue to accumulate, they could lead to extended periods of higher than normal activity. Not necessarily a single extreme event, but a sequence of events occurring closer together in time. Under those conditions, the system has less time to recover between impacts. And as the intervals between events decrease, the overall level of risk begins to rise. Not because each individual event is stronger, but because they are no longer independent. There may be no obvious change in everyday life, no clear signals, no direct indication that something is wrong. But one detail becomes easier to notice over time. Attention is usually drawn to large events, while smaller changes are often ignored. And yet, it is those smaller changes, when they accumulate, that shape the final outcome. This is not only true for the sun, it also applies to how we understand it. Most important shifts are not always visible at the beginning. Sometimes they exist as small deviations, subtle numbers, and details that are easy to overlook. But in retrospect, those details are often where the story actually begins. When a geomagnetic storm occurs on Earth, it usually begins with an event on the surface of the sun. A dark region appears, known as a sunspot. Then, a release of energy follows, which may take the form of a radiation flare or a mass ejection into space. In some cases, this stream of material, primarily charged plasma, travels toward Earth at speeds of millions of kilometers per hour. A few days later, Earth's magnetic field begins to fluctuate. This is the basic sequence of events that has been observed many times. At a physical level, the sun is not a solid object. It is a massive sphere of plasma where charged particles move continuously under the influence of temperature and magnetic fields. The temperature at the sun's core reaches around 15 million degrees Celsius, where nuclear fusion occurs, converting hydrogen into helium and releasing energy. This energy gradually moves outward through multiple layers before reaching the surface and being emitted as light and radiation. But the key factor is not just energy, it is the magnetic field. The sun generates a highly complex magnetic field, not stable, not fixed. Plasma flows continuously, dragging magnetic field lines with it, twisting them, stretching them, and at times causing them to break. These breakpoints are where major energy events occur. To predict solar activity, scientists rely on a fundamental concept, the solar cycle. On average, every 11 years, the sun transitions from a relatively quiet state to a more active one, and then back again. During the maximum phase, sunspot numbers increase. Energy release events occur more frequently. During the minimum phase, the surface of the sun becomes relatively quiet. This cycle has been observed and recorded for over a century, and for most of that time, it has behaved in a relatively consistent way. The issue is that the 11-year cycle is not a complete mechanism. It is a description, a way to summarize trends, not a system that predicts every detail with precision. In reality, each cycle can differ in intensity, duration, and distribution of activity. Some cycles are stronger than average, others are weaker. And more importantly, there are variations within each cycle that simple models cannot fully capture. When we describe a cycle as weak or strong, that is a classification, not an absolute prediction. The exact origin of the solar cycle is still being studied. Multiple models have been proposed, ranging from internal flow dynamics to interactions between layers of plasma. But no single model can fully explain all aspects of the sun's behavior under all conditions. We can predict general trends, but we cannot determine exactly when a major event will occur, especially for rare events with intensities far beyond the average. And that is the key point. Not everything on the sun follows a predictable cycle. When magnetic field lines become twisted beyond a certain threshold, they can reconnect suddenly. This process releases a large amount of energy in a very short time. It is the mechanism behind solar flares and coronal mass ejections. In most cases, these events are not directed toward Earth. But when alignment occurs, their effects can be felt days later. This does not happen continuously, but it is not uncommon. From an observational perspective, the sun appears stable. It rises each day. It emits light consistently. But beneath that surface is a complex, dynamical system, constantly changing. This does not mean that every small variation is cause for concern, but it does suggest that what we observe is only the surface of a much larger process, a process that cannot always be predicted with precision. When we look at the sun from Earth, we often see a bright, stable, unchanging disk. But that is only one perspective. From another point of view, it is a system in continuous motion, governed by dynamics we are still working to understand. And perhaps what matters is not whether we can predict everything with accuracy, but recognizing that there are still parts of this system that remain beyond our current understanding. Before Solar Cycle 25 officially began in late 2019, a group of scientists from multiple organizations, including NASA and NOAA, released their forecast. Based on data from previous cycles, they estimated that this cycle would be relatively weak. Sunspot numbers were expected to peak below average, similar to the previous cycle. Within that context, the general expectation was a relatively stable phase, with limited, large-scale variation. But starting around 2023, observational data began to show a different trend. Sunspot numbers increased more rapidly than expected. Energy release events appeared more frequently. By 2024, activity levels had exceeded several of the original forecast thresholds. Observations from satellites and ground-based stations pointed to a fairly clear outcome. Solar Cycle 25 was not following the trajectory that had been initially projected. The peak appeared earlier. The overall intensity was higher, and certain high-energy events occurred more frequently than anticipated. These were not isolated anomalies. They appeared consistently over a long enough period to be considered a trend. Solar cycle prediction models are not arbitrary. They are built on multiple layers of data: historical records, magnetic field modeling, and internal flow dynamics within the sun. Across many previous cycles, these models have provided reasonably accurate estimates of overall trends. That established a certain level of confidence. Not absolute prediction, but sufficient guidance. The key point is not that the predictions were off. It is how we interpret the level of precision those predictions represent. A model can be accurate in terms of direction, while still being inaccurate in terms of magnitude and timing. And in complex systems like the sun, the difference between trend accuracy and detail accuracy can be significant. When a cycle is described as weak, that does not exclude the possibility of strong activity occurring within it. In other words, even the best models have limits. One of the central questions now is, what caused this cycle to diverge from expectations? Several explanations have been proposed. Changes in plasma flow within the sun, variations in deeper magnetic field structures, or interactions between layers that are not directly observable. But at this point, there is no single definitive answer. This is not a sign of failure. It is a characteristic of a system that is still being studied. If a cycle can deviate from prediction to this extent, then the likelihood of unexpected variations becomes more difficult to assess. Not every deviation leads to a major event, but as predictive certainty decreases, uncertainty increases. And in systems that rely on early prediction, that uncertainty can create gaps in preparation. These changes do not directly affect daily life. There are no immediate signs, no clear indication that something is wrong. But one point becomes clearer over time. Much of our sense of control is built on the ability to predict. And when predictions become less precise, that sense of control becomes relative. This does not mean the system is out of control, but it does suggest that the stability we are familiar with is not always based on complete certainty. And perhaps it is at this point that a different line of explanation begins to emerge. When models no longer provide clear answers, there is a tendency to look for simpler patterns, longer cycles, more intuitive rules. And in many cases, those explanations begin to spread faster than the underlying data itself. Not because they are more accurate, but because they are easier to understand. And that is when another idea begins to take shape. In recent years, alongside established scientific research, another idea has begun to appear with increasing frequency. A cycle of roughly 12,000 years, often associated with major events on Earth. This idea is commonly linked to concepts such as magnetic pole shifts, global disruptions, or solar energy events far beyond normal levels. It does not originate from a single source, and it is not presented in a consistent form. But it shares one common trait. It spreads quickly, not through scientific journals, but through videos, articles, and platforms where information can be shared directly. Part of this idea is based on real data. Studies of ancient tree rings and ice cores have shown that in the past, there were unusual high-energy events. These events left traces in the form of sudden increases in isotopes such as carbon-14. Some of these events have been identified in historical records, for example, around the years 774 to 775 CE. These data points are not hypothetical. They have been measured and confirmed. When isolated events are discovered in historical data, the next step is often to look for patterns. There is a natural tendency to connect data points and form a cycle, a repeating interval, a predictable rule. In many fields, this approach is useful. But in complex systems like the Sun, identifying a simple cycle is not always possible. The difference lies in how the data is interpreted. Scientific studies indicate that high-energy events have occurred in the past, but they do not confirm that these events follow a fixed 12,000-year cycle. The intervals between recorded events are not consistent. They do not repeat at fixed lengths. Connecting these data points into a precise cycle is an additional layer of interpretation, a simplification to make complex events easier to understand. That does not make the idea meaningless, but it does suggest that the idea is not fully derived from the original data. What remains unclear is this: what exact mechanisms produced these high-energy events in the past? Are they directly linked to the Sun or to other sources in space? And more importantly, how often do they actually occur? At present, historical data is still limited. These traces only appear when preservation conditions are suitable, which means some events may have occurred but were never recorded. When a simple idea spreads widely, it can begin to replace more complex explanations. A fixed cycle is easier to understand than a system with many variables. But in the process of simplification, some information is lost. And when information is lost, the way risk is evaluated can change. Not because the original data is incorrect, but because the interpretation has reshaped its structure. There is a difference between receiving information and understanding how that information was formed. A number, like 12,000 years, can create a sense of certainty. But that sense does not always reflect the full nature of the data. This applies not only to theories about the Sun, but to how information is approached more broadly. Sometimes, a simple answer can obscure a more complex question. When the data is separated from its interpretation, another point becomes clearer. It does not take a cycle lasting thousands of years to show that the Sun is capable of producing powerful events. Because there was a moment in history when such an event was directly observed. Not through tree rings, not through ice cores, but through what people saw in real time. On September 1st, 1859, a British astronomer named Richard Carrington was observing the Sun through a filtered telescope. He was tracking a group of sunspots, a routine activity at the time. While sketching their shapes, he noticed two bright white points suddenly appear on the surface. The phenomenon lasted only a few minutes and then disappeared. This was the first time in recorded history that a solar energy flare was directly observed and documented. Approximately 17 to 18 hours after Carrington's observation, Earth began to register clear effects. The planet's magnetic field fluctuated intensely. Instruments at the time recorded changes unlike anything previously seen. Auroras appeared at unusually low latitudes, including regions near the Caribbean and South America. In some locations, the light was bright enough to read by at night. The telegraph system, the most advanced communication technology of that era, began to malfunction. Some equipment produced sparks. Certain stations reported sudden surges in electrical current. In a few cases, messages could still be transmitted even after power sources had been disconnected. At the time, the connection between solar activity and events on Earth was not well understood. Phenomena like auroras were often treated as isolated occurrences, not directly linked to the sun. Carrington's observation and the events that followed became one of the earliest pieces of evidence connecting the two. However, it took many years for the underlying physical mechanisms to be studied in detail. Even though the Carrington event is now recognized as one of the most powerful geomagnetic storms ever recorded, the way it was interpreted for a long time remained limited. Partly because of the technological context of that era, electrical systems were not yet widespread. There were no satellites, no global data networks. As a result, the effects of the event were mainly observed through telegraph systems and auroral displays. If the same event were to occur in a modern context, its impact would likely be understood very differently. Despite the available historical data, accurately reconstructing the full scale of the Carrington event remains difficult. There were no satellites to directly measure solar ejections, no global systems to record the full extent of the impact. Most of the information comes from isolated reports from specific locations, which suggests that the true scale of the event may have been larger than what was recorded. Under current conditions, a similar event would interact with a very different system. Power grids now span national and international scales. Thousands of satellites operate continuously in orbit. Data networks are globally interconnected. A strong geomagnetic storm could generate induced currents far beyond what these systems were originally designed to handle. Transformers could become overloaded. Satellites could experience failures. Navigation and communication signals could be disrupted. This does not occur in every case, but it remains within the range of possibility, based on what has already been observed. The Carrington event is not a theoretical scenario. It is a documented historical event, and that carries a simple implication. Events of this magnitude are not outside the capabilities of the solar system. They do not require unknown conditions. They have already occurred under conditions we have observed. And that leads to a different question, not whether such an event can happen, but when and under what circumstances. The Carrington event shows what is possible when a powerful geomagnetic storm directly impacts Earth. But there is another detail, less frequently discussed. In the modern era, a similar scale event has already occurred once again. Not in the 19th century, but much closer to the present. The only difference is that Earth was not in its path, and that distance was not as large as it might seem. In July 2012, the Sun released a massive coronal mass ejection, a stream of charged plasma moving through space at extremely high speed. This event did not directly impact Earth. There were no unusual auroras, no system disruptions. For most of the world, it went completely unnoticed. It was only later, when satellite data was analyzed, that the true scale of the event began to emerge. A space observation satellite, Stereo A, recorded the ejection directly as it passed its position. Measurements showed the plasma was traveling at extremely high velocity. The associated magnetic field had a structure capable of producing a severe geomagnetic storm if it had been directed toward Earth. When scientists compared this data with previous models, a conclusion began to take shape. The 2012 event was comparable in intensity and in some aspects may have exceeded the Carrington event of 1859. At the time it occurred, it was not considered a threat. There were no major alerts, no emergency response, simply because it was not heading toward Earth. From another frame of reference, it was just another solar event. What stands out is not the event itself, but Earth's position at that moment. The planet's orbit placed it just outside the path of the ejected material, within a relatively short window of time. Estimates suggest that this difference was only about 9 days. If Earth had been in a different position along its orbit, the event could have directly interacted with the planet's magnetic field. One question remains unresolved. How often do events of this magnitude actually occur? Direct observational data only spans a few decades, a relatively short period compared to the longer cycles of the Sun, which means we may not have observed long enough to fully understand the frequency of rare events. If a similar event were directed toward Earth, its effects could begin within 1 to 3 days. The planet's magnetic field would come under significant pressure. Induced currents could appear across large-scale power systems. Satellites in orbit could be exposed to elevated levels of radiation. In some scenarios, systems might be able to protect themselves and recover. In others, disruptions could last longer. Not because such an event has never happened, but because the systems it would affect today are far more complex than those in the past. The 2012 event is not a hypothesis. It is a recorded case that simply did not impact Earth. And it highlights a simple point. The distance between nothing happens and a major event is not always large, not centuries, not thousands of years, but sometimes just the position of a planet in its orbit at a specific moment. The 2012 event introduces another limit to how risk is understood. Not only what has happened in history, but what has happened without direct impact. And when this is considered alongside deeper historical evidence, a broader picture begins to emerge. Not a single event, not a single cycle, but a category of phenomena that may be more intense than anything observed in the modern era. And that is where the perspective needs to extend beyond what has been recorded in the past few centuries. Unlike the Carrington event of 1859 or the near miss in 2012, there is another type of phenomenon that was not recorded through telescopes and was not observed in real time. These events were discovered not in the sky, but in the growth rings of ancient trees and in layers of ice accumulated over thousands of years. In 2012, a Japanese researcher, Fusa Miyake, published an unusual finding. In tree ring samples dated to around 774 to 775 CE, carbon-14 levels increased sharply, far beyond normal variation. This change appeared almost simultaneously across the globe. Carbon-14 is an isotope formed when high-energy particles from space interact with Earth's atmosphere. When the flux of energetic particles suddenly increases, carbon-14 levels rise accordingly. And because trees absorb carbon as they grow, tree rings become a natural record of these changes. Data analysis shows the 774 to 775 event had an intensity far exceeding any solar storm recorded in the modern era. Subsequent studies also identified similar events around 993 CE and even further back in time. For a long time, assessments of solar risk were based primarily on observations from the past few centuries. The Carrington event was often considered an extreme case. But tree ring data suggests something different. There are events that extend beyond the reference frame we typically use. This does not contradict what we already know, but expands it. A common approach is to use recent data to estimate what may happen in the future. But when rare events are included, this method becomes incomplete. If we rely only on events from the past few hundred years, we may underestimate the possibility of higher intensity scenarios. This is not a flaw in the method, but a limitation of the input data. One key question remains unresolved. Are these events actually solar in origin? Some models suggest they may be extreme solar flares, far more powerful than those observed today. Other hypotheses point to external sources, such as nearby gamma-ray bursts. At present, there is no full consensus, which means we know these events occurred, but not exactly what caused them. If an event of similar scale were to occur in the modern era, its impact could differ from the past, not because the event itself has changed, but because the system it interacts with has changed. Satellites could be exposed to radiation beyond design limits. Power systems could experience higher than expected induced currents. Data networks could face widespread disruption. These outcomes are not guaranteed to follow a single scenario, but they remain within the realm of possibility when energy levels exceed what has been tested in the modern era. The existence of Miyake events suggests a simple point. The reference frame we often rely on represents only part of reality. Not everything that can happen has been observed in recent history. This does not mean a major event is imminent, but it does suggest that uncertainty may be greater than typically assumed. When events like Carrington 2012 and Miyake are considered together, a broader picture begins to emerge. Not a single cycle, not a single scenario, but a spectrum of varying levels of impact. And within that spectrum, there are ranges the current system can handle, and ranges that have never been directly tested. And when viewed in the context of the modern world, the question is no longer what could happen, but if it does happen, how will our systems respond? The effects of solar activity are not theoretical. Across recorded events, from 1859 to smaller incidents in the 20th and 21st centuries, technical systems have responded in measurable ways. Induced currents have appeared in transmission lines. Electronic systems have experienced interference. Communication signals have been disrupted for short periods. These are not assumptions. They have occurred on smaller scales under specific conditions. When a strong geomagnetic storm reaches Earth, its effects are not evenly distributed. Certain regions are impacted more than others, particularly at higher latitudes where the magnetic field is weaker. Long transmission lines can act like antennas, capturing induced currents from magnetic field fluctuations. Transformers, critical components of the power grid, can become overloaded when these currents exceed design limits. For satellites, high-energy radiation can affect electronic circuits or disrupt control systems. GPS signals, which depend on transmission through the ionosphere, can become inaccurate when that environment is disturbed. All of these effects have been observed in previous events. For many years, systems have been designed with protective mechanisms. Automatic circuit breakers, backup systems, load-shedding procedures. These measures are effective when events fall within expected ranges. And most of the time, that has been the case. This has led to a common assumption that systems can protect themselves in most situations. The difference lies in scale. Protective mechanisms are designed based on known scenarios, or those considered likely. But if an event exceeds those boundaries, systems may not respond as expected. An overloaded transformer does not always simply disconnect. In some cases, it can suffer physical damage, and replacing such components does not happen quickly. This does not necessarily lead to an immediate global failure, but it can create points of disruption that last longer than anticipated. One of the most difficult aspects to predict is how different systems interact under stress. The power grid is not a single system. It consists of multiple interconnected networks. Telecommunications depend on electricity. Financial systems depend on precise satellite timing. Transportation systems depend on positioning. When one component is disrupted, others can be affected. Not in a fixed pattern, but in multiple directions. If a large-scale event occurs, its impact may not come from a single cause. Some regions may lose power temporarily. Some satellites may stop functioning. Some signals may become unreliable. When these factors occur simultaneously, they can form a chain of disruptions. Not a single event, but a process. a process that takes time to recover from. Most of these systems operate in a way that users rarely need to consider. Electricity is continuous. Signals are always available. Data moves almost instantly. This creates a sense of stability and predictability. But that stability depends on multiple systems functioning correctly at the same time. When one of those conditions changes, the overall experience can shift. Not immediately, but gradually, and in ways that are not always obvious at first. These scenarios are not new considerations. For years, research organizations and agencies have been developing mitigation strategies. Monitoring satellites have been deployed. Early warning systems have improved. Some infrastructure has been redesigned to increase resilience. This does not mean the risk disappears, but it shows that efforts are being made to understand and prepare for what may happen. And that leads to the next question. How prepared are we relative to the true scale of the problem? After past events and recent observations, monitoring solar activity is no longer just a matter of basic research. It has become part of a broader forecasting infrastructure. In recent years, organizations such as the National Oceanic and Atmospheric Administration have deployed additional dedicated satellites to monitor space weather in real time. These satellites do not observe Earth, but the Sun itself and its surrounding environment. The goal is not to prevent events, but to detect them early as they begin to form. Monitoring satellites are positioned at stable locations in space, allowing continuous observation of solar radiation and plasma flow. One of the most important observation points lies between the Earth and the Sun, where satellites can detect incoming plasma before it reaches the planet. From this data, forecasting centers can issue early warnings, ranging from several hours to a few days in advance. That window, while limited, is enough to implement certain mitigation measures. With advances in monitoring technology and predictive modeling, a general assumption has begun to take shape, that we are now capable of detecting and responding to major events. Systems can be temporarily shut down. Satellites can enter safe mode. Power loads can be adjusted to reduce stress on the grid. In many cases, these measures can significantly reduce the impact of an event. The difference lies in timing. Not all solar effects arrive at the same moment. Electromagnetic radiation from a flare can reach Earth in about 8 minutes, almost instantly. Meanwhile, charged particles may take 1 to 3 days. This creates a gap. Some effects occur before any response can be implemented. Others arrive after warnings have been issued, and systems do not always have enough time to respond within that window. Current warning systems are designed based on previously observed events. But for events beyond that range, real-world performance has not been fully tested. Some measures may work as expected. Others may not be sufficient under more extreme conditions. This is not a flaw in design, but a limitation of not having experienced such scenarios in reality. In the field of power infrastructure, certain solutions have been implemented. Devices known as GIC blockers can limit induced currents entering transmission systems. They do not eliminate risk, but they can reduce stress on critical components like transformers. In space systems, satellites are designed with protective modes, allowing temporary shutdown of sensitive components when radiation levels increase. At an international level, projects such as the Vigil mission by the European Space Agency are being developed to observe the Sun from different perspectives and improve forecasting capability. These efforts point to a clear conclusion. We are not entirely passive. There are tools being developed, systems are being improved, and in many cases, they have proven effective to a certain extent. This significantly reduces the likelihood of severe disruptions in common scenarios. However, there is one point that remains important across the entire picture. Protective systems work well when events fall within the range they were designed for, and when that range is exceeded, their effectiveness can no longer be assumed. In other words, what has been built can help reduce risk, but it does not fully eliminate the possibility of events beyond what we have previously experienced. And that is where the final question begins. When looking back at everything that has been recorded, from unusual auroras in 2024 to minor system deviations from the Carrington event to 2012, and further traces found in ancient data, one point becomes clearer. None of these events are entirely isolated. They are data points within the same spectrum of solar activity. The sun does not operate randomly. It has cycles, structure, patterns that have been studied for decades. Current models allow us to understand much of its behavior at a level sufficient to predict general trends. But understanding most is not the same as understanding everything. There are still variations that do not follow simple patterns. In the modern world, the ability to predict creates a sense of stability. When a system can be modeled, it becomes familiar. And once it becomes familiar, it begins to feel controllable. This applies to many technical systems, but not all. A model is always a simplification of reality. It helps us understand, but it cannot fully replace what it represents. When models perform well over long periods, it becomes easy to assume they describe the entire system. But even small deviations suggest that parts of the system remain unaccounted for. We still do not know the exact frequency of the largest events. We do not fully understand the mechanisms behind events like Miyake events, and we cannot precisely predict when extreme variations will occur. This is not a lack of progress. It is a natural characteristic of studying a system at the scale of the sun. What has been observed reveals a wide spectrum, from minor fluctuations to events capable of large-scale impact. Most of the time, the sun operates within the stable range of that spectrum, but not always. And when an event moves toward the higher end of that range, its impact depends heavily on the system it encounters. The stability we experience is not a fixed state. It is the result of multiple conditions operating within acceptable limits. When those limits are maintained, systems function smoothly. When one of them shifts, the system can respond. This does not mean disruption is inevitable, but it does suggest that stability is not the default. When we look at the sky, the sun still appears each day in the way we have always known. Its light does not seem to change. Its cycle continues. But at another level, it is not a static system. It is always in motion, always changing, and not always within the range we can precisely predict. And perhaps what matters is not trying to fully control such systems, but recognizing that we exist within a system larger than ourselves, one that does not need to conform to what we expect. If you are still listening at this point, you may have realized that the question is not only about the sun, but about how we understand and the limits of that understanding. And perhaps that is a natural place to pause.